of radio astronomy, although not very recent. This is the 20th anniversary of the first fringes from long baseline interferometry. In the early 1960s, there was great excitement among radio astronomers in Canada. In 1960, the DRAO at Penticton had been commissioned. The National Research Council was planning and starting to build the 46-meter telescope at ARO. And there was another large dish operating in Canada that was at Prince Albert, the Prince Albert Radio Radar Laboratory. A number of astronomers, or radio astronomers at that time, were thinking of the possibility of combining these three large instruments, that is, operating an interferometer using these three instruments. Actually, nothing came of these discussions or ideas until Herb Gush at the University of Toronto advanced the idea of independent recording of the signals and later playback. And of course, this is the principle of long baseline interferometry. Herb was in the physics department of the University of Toronto at the time and discussed his ideas with several people, including John Galt, who is on the program this afternoon, and Alan Yen, whom we hope will be on the program later this afternoon. But the initial idea was Herb Gush's, and he put down these ideas in a report which is entitled Study of a Long Baseline Radio Interferometer in August of 1965. And that marked the beginning in Canada of the concept and the working towards a working model of long baseline interferometry. Herb Gush is now a professor at the University of British Columbia, so he has come some distance to be with us today. It gives me great pleasure to ask him to introduce this session this afternoon.
Thank you, Jack. I would like to thank Dr. Feldman for organizing this conference on early radio astronomy in Canada and for inviting me to participate. He asked me to share with you my recollections of the beginnings of the long baseline interferometer work. Because my memory is far from perfect, I've had to rely nearly entirely on documented material. And so my presentation will consist of a number of slides of notebooks which I kept at the time, showing different stages of my involvement. I don't expect you to read all the stuff which goes on the slide. I'll be pointing out a few key dates or phrases. I think my interest in radio astronomy stemmed from undergraduate work at the University of Saskatchewan, where I gave in 1951 as part of a required seminar program a seminar on the beginnings of radio astronomy and the recent discovery of the 21 centimeter line of hydrogen in an astronomical source. My interest did not develop in a professional sense in radio astronomy. Nevertheless, I maintained an interest in it and visited various radio observatories in both Europe and in Australia. And the visit to Australia took place in 1964, where I saw the intensity interferometer of Hanbury, Brown and Twiss. The reason I mention that will become clear in a moment. The impetus for my interest in making a large interferometer in 1964 came from the identification in the early 1960s of quasi-stellar objects. If the assumed distance of these entities was correct, their energy output was enormous, and it was clearly important to try to understand them. And it was also clear that a better measurement of their angular diameter was essential, and this required the use of radio interferometers whose baseline significantly exceeded those currently in use. The problem in making such a device work was the phase instability in the links connecting the different arms of the interferometer to a correlator. because the intensity interferometer, which I just mentioned, is less sensitive to these phase instabilities, I first considered this as a possibility, and for my own purposes did an extensive theoretical analysis of the device. This is illustrated in the first slide. This is from my notebooks, and the date is November the 6th, 1960, and the only thing of relevance here is this sketch of the intensity interferometer and how it works. It became apparent from this analysis, and of course also from the analysis which Hanbury, Brown, and Twist themselves made, that for this, the purpose I had in mind, the observation time required to make a measurement was impractical. And so then I again began to examine the amplitude interferometry. I spent time thinking about this in the winter of 1964, but the first written material with dates on it occurs somewhat later. If I could have the next slide. So this is an item in March 31st, 65, and I say here that on about March the 15th I had a discussion with Gordon Shepherd, who was then at the University of Saskatchewan, concerning the possible use of the Penticton radio telescope and the Prince Albert radar as a long baseline interferometer. It also reports here that I saw about that time John Galt, who was visiting Toronto, and he was quite interested in the proposal, but he was somewhat skeptical that it would work because of this phase instability which I just mentioned. The next slide, please. So this will be a sequence of slides from these entries in my notebook, in which here I have drawn a standard diagram of a radio interferometer showing the rotation velocity of the Earth, that this signal is Doppler shifted upwards and this one downwards in frequency, and this showing then what kind of frequency of fringes you got. One of my problems was that with really long baselines, the fringe frequency was high, and you had problem doing measurements at large bandwidth. Next slide, please. Here was an ideal type of fringe pattern that you would get if you had a large bandwidth, and the problem is that this moves very this peak in the correlation function moves very rapidly due to the rotation of the antennas. And I understood that you get rid of this by injecting phase shift in one side and subtracting phase shift from another side. The next slide, please. I think that it's in this slide that the most relevant material is contained. So it says here, under normal operation of the interferometer, a local oscillator is used at each antenna to reduce the frequency of the signal of interest to a minimum, say a few megacycles. Now it should be possible to record the signals at each station and correlate them afterwards. Provided that the local oscillators are stable and the frequency is known, this should be a perfectly valid technique. So then it says next, the problem is how to use a wide band. That is, how to cancel the Doppler shift, and it says this can be done in principle by playing back the records at slightly different speeds. So if beta equals V over C, where V is the velocity of the antenna, you shift one speed up by 1 plus beta, the other by 1 minus beta. So this is the heart of the technique. The next entry in my book, dated 2 days later, if I could have the next slide, says that I saw Alex Kavadas at the airport. Alex Kavadas, some of you may know, was the director of SED Systems at Saskatoon. Maybe at that time he was at the University of Saskatchewan. And I discussed this large baseline interferometer with him, and he was quite interested, but not from the astronomical point of view, but from the point of view of measuring fluctuations in the plasma density at very high altitudes. And so the part of the work of the PA radar was devoted to research purposes, and so he was quite interested in applying the radar unit to that work. It says here that it seems to me that the correlation must be done in a computer, because the problem of correlating wideband signals from independent tape recorders looks very severe. On the other hand, I have here a sketch of an apparatus which I thought could be used to stabilize the frequencies coming off of a tape recorder. It turned out that later that commercial tape recorders having this scheme actually were developed and available commercially. I guess the next slide shows a further development in my thinking. Let's see, where does it say it? The signals are recorded on tapes, and on a parallel track is recorded a reference sine wave derived from the stable local oscillator. Signals are digitized using a reference sine wave as a triggering source. This technique was not actually used in the Canadian system, as we'll see in a few minutes, but I believe it was the one used in the American system, which was developing at about the same time. The next slide is dated July the 6th, 1965, and here I made a study of just how long it would take to correlate digital signals in the existing computer at Toronto, which was an IBM 7094. There's a kind of faded printout of the program and some estimate of the amount of time that it would take to do this, an actual correlation. It turned out that it was a reasonable amount of an amount of time that one could consider in doing a practical experiment. Could I have the next slide, please? The first more or less formal statement of these ideas was in a very brief report titled "Long Wavelength Interferometer," a long baseline radio interferometer for the measurement of quasar diameters, dated June 1965. I don't have the original of that for some reason. And this was just a kind of formal summary of the ideas which I've been putting in notebooks. On the next slide shows the first page of this report. And the only relevant thing here is that up here I said, well, we could use Penticton and Prince Albert. And here is the key sentence. The novel feature of the proposed interferometer is that the radio signals will be recorded on magnetic tape at each antenna, and the signals will be correlated after recording using a high-speed digital computer. In this way, no radio link or cable is required between the two sites. On the next page, there is a next slide, please. There is a list of equipment, but that's irrelevant for our in the current context. I said here it's expected that a number of institutions would be interested in this experiment, and it lists John Galt from Penticton, Cavadis from Saskatchewan, and Dr. Yen from the University of Toronto. Now, what is not written down in my notes anywhere is the extent of my discussions with Alan Yen, and I know that I had some, but I don't know at what point they occurred in this stream of events. The next stage of the development was a more formal report, a larger report than this one, which I could have the next slide. That's the one which Jack Locke referred to a few minutes ago, a rather detailed study of the proposed interferometer. That is a study from a theoretical point of view. It's prepared when I was at the University of Toronto. Although this is quite a detailed study, it never got published. And I think the reason was that all the study in the world wouldn't make any difference if you couldn't make the thing work in practice. And the big unknown at that moment was the effect of ionospheric fluctuations in the thickness of the ionosphere and whether or not this would wipe out the fringes. Once the apparatus was put together and tested and it actually worked, the study became irrelevant because everything worked. And so that's the reason, I guess, it never got published. It was, of course, circulated to the members of the group who were involved in the experiment. Could I have the next slide, please? Well, well, there is some justification for the experiment there. It's proposed to use, much like the first one, and I guess the important point here is that using a 7094 machine, 2 signals, etc., it could be correlated in about 60 minutes of computer time. Yes. The next page just shows, the next, not page, but the next slide just shows the kind of nature of this report. Here is a chapter on the timing accuracy required in the correlation calculation. This report was followed by a brief report authored by Alan Yen and myself in August the 17th, 65, and then a slightly enlarged proposal based on that one in October the 20th, 1965, if I could have the following slide. So this is October 20th, 65, proposed long baseline interferometer for the measurement of quasar diameters by Gush and Yen. This gives a more formal proposal, that is, insofar as hardware and that kind of thing is concerned. Also, there was an elementary discussion of the principle, and that's illustrated in the next slide. So here is shown the progression of thinking in the experiment. In the top picture, one has a simple dish with a receiver at the focus, and as some source passes through the field of view, you see a rise and fall in the signal. If the dish is split into 2 parts, but still with 1 receiver, again, as a source goes overhead, you see a signal which goes up and down. However, there are oscillations due to interference between these 2 parts of the dish. These are like in optics, young double slit experiment fringes. From this idea, one develops the idea of having independent receivers at the 2 dishes and sending the signals to a correlator, and you get just the same pattern as you have here, except possibly for differences in noise. And so then the next step, which is the one we were proposing, was to cut this link, record the IF signals from independent antennas on tape, and then bring the 2 tapes together and correlate them, producing this pattern. Could I have the next slide, please? Here there is however, a development on what I had been proposing earlier, and this was concerned the way the correlation was done. It says the method of recording individual signals on tapes and then correlating the tapes has become feasible only within the last few months as a result of technological advances in tape recorders and frequency standards. And so it was Alan who was pushed for doing analog correlation from the tapes and skipping this digital correlation which I had envisaged using a high-speed computer. Then following there, we examined just what kind of telescopes were available in the country, the receivers, and so on. The next slide, please. This is a report on a meeting that was held at the Prince Albert Radar facility, the first meeting of a group of people who were interested in pursuing this line of work. And they include Norm Broughton, John Galt, myself, Ted Hartz, Alex Cavadas, Jack Locke, McAlpine, Jack Meek, Seaman, and Alan Yen. The next slide, please. That was October 7th, 65. At this meeting, Alan Yen pointed out that we should try and involve the group at Queen's University who had been overlooked at this stage, and we wrote formally to Chisholm and Hughes ask them to participate. John Galt was secretary at this meeting. Could I have the next slide, please? Things progressed, and a little bit later, the 6th of December in '65, things seemed to move very fast in those days. There was a meeting at NRC to discuss details, and that was attended by quite a few people, including Vic Hughes this time, and Chisholm, and most of the people who had been at the first meeting. The next slide, please. I think somehow we went backwards there. This is the last bit of documentation which I have, which was a progress report in February of 1966. Things were developing hardware-wise, and this was bringing everybody up to date where we were. I did a little bit of work on a special purpose correlator. I think there's an illustration of that in the next slide. And so I devised this high-speed digital correlator, but I don't think it was actually used. I had also some other schemes envisaged. So this could just put the lights on a moment and shut that off. So this practically terminates the actual documentation which I have on the experiments, because from that point onwards I didn't participate as much as I had previously, because the development, the hardware development, all the wiring, testing of tape recorders and so on, was done by others, particularly Alan Yen and Norm Broughton and the group from Queens. So I participated strongly up until the first observations, which were at Penticton. I went from UBC to Penticton when we made the first measurements. And then I didn't participate actively in the further developments, and the reason was not that I didn't like the field or didn't get along with people, but because it became apparent to me that I had to make a strong career commitment to either astronomy or geodesy in order to exploit this development. One had to understand what sources to look at, one had to what kind of measurements to make, what frequencies to use, and so on. And I just didn't have enough background in that field. I didn't have enough background either in geodesy, what continents was interesting to measure distances between, and so on. On the other hand, I'm still interested in the measurement of diameters of astronomical entities. And just to conclude with two slides, I'll just show you a bit of further development, which doesn't have to do with long baseline experiments, but it came out of that work, really. First one, next slide, please. Here's a paper on imaging in the optical region using aperture synthesis to get very high resolution in the optical region. And on the next slide, there's an illustration of a return, really, to the classical Michelson interferometer in the optical region, the novelty being that one can measure the diameter simultaneously at a wide number of frequencies. Well, that's all that I have to say, and it's been a pleasure to address you. I hope I haven't bored you too much.
I'd just like to ask about the original ideas. I was with Paul Feldman, of course. I got the impression Paul Feldman was a fair part in some of the early discussions. In fact, maybe one of the major people who put forward the major ideas on baseline interferometry. But you don't seem to mention him in your with one of the original.
No, I personally had no contact with Bob Chisholm, so I was not aware of what his activities were until as I pointed out, he was invited to join the group, then I had contact with him prior to that. So he may very well have been having had parallel developments.
I'd like to say a word to that point. The antenna department of Queens has a report by Dodge in 1959 in which he talks about operating independent receivers. I wrote a letter to George Harrow where he feels the way that Hughes commented. And sometime in 1962 or 63, Bob spent 6 months or so in my office. Tom Legg was around. I wish he were here to my office. And I can remember Tom and Bob at the blackboard trying all sorts of combinations of detectors and so on. So I'd like to just support what Nick said. But what you've done is excellent because it's part of the ongoing stream.
Because I'm just unfamiliar with what did.
Could I just add into this as well, that you went over to the electrical engineering department at one time, you couldn't get in the blasted place because CBC tape recorders were all over the place. And I think it was Bob who did some of the major parts of getting those tape recorders to work. As far as the
I said I didn't participate personally in the hardware part.
It's certainly true that Bob did a major part of the work in developing the tape recorders for use.
We also, incidentally, as a matter of interest, there was I think it was an SC meeting in the late 60s when we were trying to set up an interferometer, ideas for interferometers between Algonquin and Kingston, and the mobile dish in between. And there were discussions going on about interferometry, and I think we kind of said, what about can we reserve a satellite, or could internationally we reserve a satellite to tie up these bases? And everyone said, be quiet, we've got far more, more detailed stuff to deal with at the present time. That's something for the future. But that was the late 60s.
I think in the early 60s, many people were thinking about how to make an interferometer along the space line. I recall at a meeting, or at the opening, the official opening of the DRAO, we discussed the possibility of combining Penticton and Prince Albert. But we didn't come to any conclusions. And I think it was her who really put the ideas down, the ideas down on paper, and got us moving.
I was supporting that. I remember Susan getting up and discussing it as a whole.
Yeah.
And nothing was done. So, well, then there'd be the paper from the Department of Electrical Engineering. In my article in Sullivan's book, I do mention this specifically as part of the development of on-baseline telemetry. Well, Chisholm then went to Australia for working with Chisholm, Christensen.
They were thinking about it in Russia at the same time, too. There's an early paper in Russian literature on long baseline interferometry, theoretically. Yes.
Jack, I remember a meeting that was held in the Gal Rake building at U of T one Saturday morning. And I think you must have been there. And Chisholm, Alan Yan, John Gull, I suppose. And the purpose of this meeting was to make a final decision to go or not to go. Do you remember the date of that meeting?
I have it in my notes, I think. I should look it up, I think. At that time, we were looking for support.
Yes.
And we asked the Canadian Nursing Committee for support, and Dick was chairman, I think, of the committee at that time.
Actually, Dick Retty, I was chairman of the Canadian Commission for Biodiversity, and Dick Retty asked me to look after and organise the meeting. I called
Yes,
up.
and the Committee on Astronomy at the Dominion Observatory, Committee on Astronomy at the Department of Engineering and Resources, was asked for its support and gave it unqualified support for a go-ahead. Well, if there are no further comments, I thank you very much, Herb, on behalf of the group for your contribution. As Herb